This is a review for chapters 13 and 14, which were about chance and probability. So example 131, an elementary school class has 12 boys and 13 girls. 2 children are chosen at random to lead the sports teams. So number 1, what is the chance that both of the children are girls? So we're looking for the probability that you get a girl and then a girl. So because that's an and, we know we're going to times. So if there's 12 boys and 13 girls, that's 25 total. So if we want the probability of a girl, there are 13 girls out of a total of 25 students. Times, okay, now I need to get a second girl, but I've already chosen one girl, so there's only 12 girls left and only 24 students total. So I put this in my calculator. My calculator tells me that this is 13 out of 50, or if I change it to a decimal, 0.26. Number 2, what is the chance that both of the children are boys? So if we look for the probability that we get a boy and then a boy. Now again, because that's an and, we know that we're going to multiply our probabilities. So if I want a boy, there are 12 boys out of 25 for my first boy. But now for my second boy, there are only 11 boys left and only 24 total children. So this gives me 0.22. You might notice that this is the first time I've been writing my chances in decimals. I'm just doing that because I'm getting kind of big, nasty fractions. Some of us will probably simplify, some of us probably won't. Decimals are just easier for all of us to get the same answer. Number 3, what is the chance that the first is a girl and the second is a boy? So we want specifically to get a girl and then a boy. So if I want to get a girl, there are 13 girls out of 25. Now I want to get a boy. There are still 12 boys, but only 24 children, because I already chose one child. So this gives me 0.26. Now I want the chance that the first is a boy and the second is a girl. So the probability of a boy and then a girl. So for a boy, there's 12 boys out of 25 children. Now I want a girl. There are 13 girls, but only 24 children because I already chose a boy. And this gives me 0.26. Now number 5, we're going to make it more complicated. So what is the chance that one of the children is a girl and the other is a boy? So that means we're looking for the probability of girl-boy, or you could do boy-girl. Now luckily for us, we already found those two probabilities in 3 and 4. Now we just have to add them together. We add them because it's an or. So this is 0.26 plus 0.26, which gives me 0.52. So see above for how we found those probabilities. Number 6, what is the chance that at least one of the children is a girl? So for this, we can say, okay, what are the ways that we can get at least one child to be a girl? You could do girl, girl, or girl, boy, or boy, girl. And then you just have to go up and find each of those probabilities and add them together. So girl, girl is 0.26, plus girl, boy is 0.26, plus boy, girl is 0.26, which gives me 0.78. That's method number 1. You could also use method number 2, which is technically faster and easier, which is to use the complement rule. The complement rule says that the probability of at least one girl is equal to 1 minus the probability of no girls. And how do you get no girls? The only way to get no girls is if you get boy, boy. So all we have to do is 1 minus the probability of boy, boy. Look up above, the probability of boy, boy was 0.22, and together that gives me 0.78. Sorry, this was supposed to be 0.78 on our first method. I just wrote the wrong one. So either way, we get the same answer. Technically, the complement rule is a lot faster because if I hadn't already found those 3 probabilities up above, it would have saved me a lot of work. Now number 7, what is the chance that the children have the same gender? So the only way you can get the same gender is if you're boy, boy, or girl, girl. Because as an or, you can just add those 2 probabilities. So probability of boy, boy, plus the probability of girl, girl. So probability of boy, boy was 0.22. Probability of girl, girl was 0.26. So this gives me 0.48. Now, just as a note to you, just blindly multiplying chances can result in trouble. Make sure you're using your conditional probabilities unless you know the events are independent. What I mean by that was coming up to say like number 4, or let's come up to number 1, that's a better example. When we had the probability of girl, girl, we had to do 13 out of 25 times 12 out of 24. We couldn't just do 13 out of 25 times 13 out of 25 because the probability of the second girl was different, and so I had to use my conditional probabilities. Now example 132, a box contains 2 red marbles and 3 yellow ones. You want to reach in and choose 2 marbles without replacement. So first, the chance that this first marble is red would be, well, 2 out of 5. And the chance that the second marble is red is, again, 2 out of 5. Remember, we did the proof for that at the end of chapter 14. And the reason why is you don't know anything about the first marble. So we go with the unconditional probability, or kind of our original probability. Number 3, the chance that the first marble is red and the second marble is yellow. So the first marble is red and the second marble is yellow. First marble is red is 2 out of 5. Second marble is yellow would be 3 out of 4. So 6 out of 20. Number 4, the chance that the first marble is yellow and the second marble is red. So the probability of yellow and then red. So the probability of the yellow one is 3/5, and now I want a red one, and there's 2 reds, but only 4 total, so 6 out of 20. Okay, number 5, the chance that one marble is yellow and the other marble is red. So now they don't care about the order. So technically this means I could do red, yellow, or yellow, red. And notice we found those 2 probabilities in numbers 3 and 4. So if I wanted a red, yellow, that would be 6 out of 20. And the yellow, red is 6 out of 20, so that gives me 12 out of 20. Now example 133 is exactly the same, except now we're doing it with replacement. So let's see how that changes our answers. The chance that the first marble is red is 2 out of 5. The chance that the second marble is red is 2 out of 5. The chance that the first marble is red and the second marble is yellow. So the probability of red and yellow. So I want a red one, which would be 2 out of 5, and then I want a yellow one, which is 3 out of 5, because I put my first marble back, so we still have 5 to choose from. So 6 out of 25. The chance that the first marble is yellow and the second marble is red. So probability of yellow and red. So there are 3 yellows, and then I put it back, and now there are 2 reds out of a total of 5. So 6 out of 25. So the chance that one marble is red and the other marble is yellow is going to be what? So now we don't care about the order, so we're interested in red, yellow, or yellow, red. So we have to add those two probabilities. So 6 out of 25 plus 6 out of 25 gives me 12 out of 25. For our next example, we have a deck of cards that's shuffled, and the 2 cards are drawn without replacement. So we don't put our first card back. So number 1, what's the probability that both cards are aces? So we need to get an ace, and then we need to get another ace. So that means we're going to need to times our probabilities. So to get my first ace, that's 4 out of 52. Times, now I need to get my second ace, but there's only 3 aces out of a total of 51. So that's 0.00452. Number 2, what's the chance that the first is an ace and the second is a king? So we need to get an ace and then a king. So to get an ace, there are 4 out of 52. Now you want to get a king. There's still 4 kings, but only 51 cards. So that would be 0.006. Number 3, what is the chance that the first card is an ace and the second card is not an ace? So this one's different, so we want to get an ace, and then we want to get a not ace. So to get an ace, there are 4 out of 52 cards that are aces. Now I want to get a not ace. There are 48 cards that are not aces, but only 51 cards left because we already drew our ace. If I multiply those two probabilities, I get 0.0723. And number 4, what is the chance that at least one of the cards is an ace? Now this one you have to do using the complement rule. There is no way you would do this not using the complement rule. It would take way too long because you would have to figure out, I don't know, thousands of possible outcomes, find each of the individual probabilities and add them up if you were trying to not use the complement rule. So let's use the complement rule. So the probability of at least one ace is equal to 1 minus the probability of no aces. So again, anytime you're looking for the probability of at least one ace, use the complement rule and do 1 minus the probability of none. So how do you get no aces? You've drawn 2 cards and you want no aces. So that means you get a not ace and a not ace. So the probability of getting a not ace, there are 48 non-aces out of 52 cards. Times, for the end, and now you want to get another not ace. There's only 47 not aces left out of a total of 51. Put all this into your calculator and you get 0.1493. For our next example, a poker hand consists of 5 cards. What is the probability that you are dealt 2 queens followed by 3 twos? Now, by default, anytime you're playing with cards, you're going to be doing it without replacement. Because if you want to have 5 cards in your hand, obviously you're not putting 1 card back before you draw another one. So we want to get a queen, and then a queen, and then a 2, and then a 2, and then a 2. And because those are ands, we're going to be multiplying. So first I want a queen. There are 4 out of 52 queens. Then I want another queen, but now there's only 3 queens out of a total of 51 cards. Now I want a 2. There are 4 twos to start with, but only 50 cards because we've already drawn 2 queens. Now for your next 2, there are 3 to choose from, but only 49 cards. And then for your next one, there are 2 twos, but only 48 cards. So this gives me about 1 out of 1,082,900. Very small number. Or 0.000000923. Number 136. A coin is tossed 5 times. Which outcome is more likely? Head, 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 or tail, head, head, tail, head? Now people look at this and they tend to think that tail, head, head, tail, head would be more likely because it seems more random, whereas head, 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 that seems very unlikely. But let's actually calculate it. So if I want the probability of head, 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 head. Those are ands in there, so head, and head, and head, and head, so we're going to multiply. So the probability of heads is 1/2. The probability of the next head is 1/2. The probability of the next head is 1/2. The next head is 1/2, and the next head is 1/2. Notice that even if I was getting head, 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 the probability of getting my next head is always 1/2 because coin flips are independent. They don't affect each other. So this is 1 out of 32. Now let's find our next probability. So tail, head, head, tail, head. So again, we're going to multiply. So probability of tails is 1/2. Probability of heads is 1/2. Probability of heads is 1/2. Probability of tails is 1/2. And probability of heads is 1/2. So we get 1 out of 32. And so they are equally likely. And again, the reason why is that coin flips are independent. So one coin flip does not affect the next coin flip. So no matter how many heads you've gotten in a row, the probability of the next head is always going to be 1/2. In our next example, we have a certain family with a father that has blue eyes and the mother has brown eyes. According to a simple genetic model, the chance of a child of theirs having blue eyes is 25%, and the chance of the child having brown eyes is 75%. Now, each child's eye color is independent from the other children, so the first child does not affect the second child, etc. So let's just make ourselves a note. So the probability of blue equals 0.25. The probability of brown equals 0.75. Now you might notice that I changed these numbers to decimals instead of percentages, and the reason why is that many calculators will do percentages wrong. If you put it all in as decimals, you know that you're going to be correct in your calculations. So number 1, what is the chance of them having 4 children all with blue eyes? So we're looking for the probability of blue, and blue, and blue, and blue. So the first child, being blue, had a 0.25. Now what's the probability of the next child being blue? Now because each child was independent, so the first child doesn't affect the second child, the probability of it being blue is still 0.25. And the next child is still 0.25. And the next child is still 0.25. If I put this into my calculator, I get 0.0039. Or you could even change it back to percent. So this is 0.39%. So there's only a 0.39% chance that all 4 children have blue eyes, even though the chance of one child with blue eyes was 25%. By the time you get to the chance that the first one is blue, and the second one is blue, and the third one is blue, and the fourth one is blue, you're down to a 0.39% chance. Okay, so number 2, suppose that they had 4 children with blue eyes and a 5th baby is now on the way. What is the chance that this baby will have brown eyes? So you might think that that would be very likely because they already had 4 children with blue eyes, and that was very unlikely, only as 0.39% chance, and you might think, oh, they're due to have a child with brown eyes. But each kid's eye color is independent, so they don't affect each other. So it doesn't matter how many kids already have blue eyes. The chance of the next baby having brown eyes is always 75%. Now this is assuming that each child's eye color is independent. We did say for a certain family. That's not saying that due to genetics babies' eye colors are always independent. That may or may not be true. I'm not a geneticist. But for this problem, because we said they're independent, the chance of the next baby having brown eyes is always 75%, no matter how many kids already have blue eyes. Now for example 138, let's roll 3 dice. These are just basic 6-sided dice. So what's the chance that we get a 1 and a 1 and a 1? So we're looking for the probability of a 1 and a 1 and a 1. So we're probably getting a 1. It's a 6-sided dice. There's 1 1 on there, so 1 out of 6. Now for my next dice, it's also going to be 1 6. And my next dice is also going to be 1 6. So I get 1 out of 260. The reason why those probabilities didn't change is that dice rolls are independent. So one dice roll does not affect the next dice roll. Number 2, what's the chance of getting no ones? Well, to get no ones, we're looking for the probability of a not 1, and then a not 1, and a not 1. Because those are ends, we're going to multiply. So if I want to get a not 1, there are 5 not 1s out of a total of 6. My next one is 5 out of 6, and my next one is 5 out of 6. So this gives me 125 out of 216. And number 3, what is the chance of getting at least 1 1? Because of the at least 1, you know that you want to use the complement rule. Because the probability of at least 1 1 is equal to 1 minus the probability of no ones. So to get no ones, you need to have a not 1 and a not 1 and a not 1. Now in number 2, we already figured that out. So that's 125 out of 216. Where we found the probability of not 1, and not 1. So this final answer is 91 out of 216. That's the probability of getting at least 1 1. And at this point, we're already doing a review, but we're really just practicing over and over. So for 139, 2 tickets will be drawn at random without replacement from this box with an RWBG. What's the chance of drawing an R first and then a B? So I want the probability of R and then a B. So to get an R, there's 1 R in there out of 4. Now I want to get a B. There's only 1 B, but only 3 possible tickets because we didn't put it back. So 112. For our next example, someone reaches into the following box with his left hand and draws 1 ticket at random. Then reaches in with his right hand and draws another ticket. So this would be without replacement. And this is from the box BGR. So number 1, what is the chance that he gets a red in his left hand? Well, that would be 1/3. Let's see, number 2, what's the chance that he gets the G in his right hand? That would be 1/3, because we didn't say anything about what he got in his left hand. So once again, you can use just that unconditional probability. Now let's change it up though. What is the chance that he gets the G in his right hand if you know that he already got the R in his left hand? So if you know that he has the R in his left hand, then there's only 2 tickets left. And so the probability of the G is only 1/2. Number 4, what is the chance that he gets the R in his left hand and the G in his right hand? So now we're looking for the probability he gets the R and then the G. So the probability of getting an R was 1/3. But now he already pulled out the R, he didn't put it back in, so now he wants to get the G, so there's only 1 out of 2 tickets left. So this would be 1 out of 6. Example 141. 2 tickets are drawn from the following box, 1, 2, 2, 3, 4, 4. There are 2 options. Which option would you choose? Number 1, if at least one of the tickets is a 2, you win $1. Or the second option is, if the first ticket is a 2, you win $1. So which one is going to be better for you? Which one are you more likely to win on? The first one. The reason why is that it is less restrictive. You just need a 2. You don't have to get, or let's put it this way, you can get the 2 first or second. Either way, you still win the $1. So the first option would be better. Example 142, 6 tickets will be drawn at random from the box RWBG. Number 1, if we draw with replacement, what is the chance of getting 6 R's? So we are specifically looking for the probability of getting an R, and 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 an R. So what is this going to give us? The probability, notice we're doing it with replacement this time. So the probability of getting an R is 1/4. Then I put it back, so now I want to get another R. That probability will still be 1/4. And I put it back, so the probability of getting my next R is 1/4, 1/4, 1/4, and 1/4. This gives me 1 out of 4,096, or 0.000244. So very small chance. Now number 2, if we draw without replacement, what is the chance of getting 6 R's? So the probability of getting R and R and R and R and R and R. So that I reach in, the probability of my first R is 1/4. Okay, now I don't put it back, and I reach in and I want to get another R. But there are no more R's. So that probability is 0. And technically the next one will be 0, and the next, and the next, and the next. So we get 0. The reason why is because you can't get more than 1 R because there is only 1 R. So this would be impossible. So the probability of any impossible thing is always 0. Okay, number 3, if we draw 6 tickets with replacement, what is the chance that at least one of the draws is an R? This sounds like the complement rule, right? So we're looking for the probability of at least 1 R. That's equal to 1 minus the probability of no R's. And how are we going to find this? We're going to have to do 1 minus the probability of not R, and 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 not R. So what is this going to be? There's an RWBG, so the probability of getting a not R, there are 3 out of 4 choices. And then I want to get another not R. And remember, this is with replacement, so we put everything back, so it's always 3/4. And then another not R, and another not R, and another not R, and another not R. So when I multiply all this out and do the subtraction, it's 0.822. So the probability of at least one R is 0.822. Now we want to roll 2 dice. Number 1, find the chance that both of the dice show 1 spot. So the probability we want to get a 1 and a 1. Well, to get a 1, that's 1/6 chance and a 1/6 chance. So 1 out of 36. Number 2, find the chance that neither of the dice show 1 spot. So now we're looking for the probability of a not 1 and a not 1. So there are 5 choices that are not 1s, and the second time there are 5 choices that are not 1s. So 25 out of 36. Number 3, find the chance that at least one of the dice shows 1 spot. So this sounds like the complement rule. The probability of at least 1 is 1 minus the probability of no 1s. And to get no 1s, we're rolling our dice twice, so we need to get a not 1 and a not 1. So this will be 1 minus the answer that we found up in number 2, because that was not 1 and not 1, so 1 minus 25 out of 36, which should give me 11 out of 36. And number 4, find the chance that exactly one of the dice shows 1 spot. Well, how can you get exactly one of the dice showing 1 spot? There are 2 options. You can get a 1 and not 1, or you can get a not 1 and a 1. Now remember, we're going to multiply for ands and add for ors. So to get a 1 and not 1, that would be 1/6 times 5/6 plus for the or. Now for not 1, that's 5/6, and for 1, that is 1/6. And this gives me 10 out of 12.